Welcome everybody to this week's edition of HoloTube, the standard edition. Yesterday we had a discussion edition, and today we have Andy Lucas from the University of Colorado at Boulder. Beautiful place, and he's going to tell us about disordered quantum critical fixed points from holography, as you can read from the slides. Andy, the mic is yours.
Okay. Yeah. Well, thanks for the introduction. Yeah, and feel free to interrupt if you have any questions or comments or something. So I'm in full screen mode, so I can't see the chat. But okay. Anyway, yeah. So I'm going to sort of, talk in some sense about some recent work with my excellent PhD student Xiaoyang and my own PhD advisor Subir. Uh, that's sort of the goal of the talk, but I'll actually probably spend a bit more time talking about some earlier work with my former student Kaushik and colleague Leo, because it kind of provides some important build up and kind of background to some of our more recent results. So, okay. The problem that this talk will try to address is kind of a long-standing challenge in quantum field theory, which is to find some kind of tractable IR fixed points, right, of the renormalization group with strong coupling, finite disorder, and ideally also some conserved charge and a finite density of that charge. And this problem is motivated, at least to me, by experiments on the so-called non-Fermi liquids or strange metals, where we believe that all three of these ingredients are present. These are sort of complicated, disordered materials, with chemical formulas that have X's in them for impurity density. So microscopically they're extremely disordered. They are strongly coupled. There are experiments that suggest there are sort of no well-defined excitations. And these are certainly systems that have, some finite density. So we would like some kind of toy model for a fixed point of RG that has all of these features. And okay, this is sort of a very hard problem a priori, but over many years, we've come up with some tricks for trying to tackle all of these points. So probably familiar to this audience, the strongly coupled problem we can address by attempting to use holography or ADS CMT to describe strongly coupled theories. And that also makes the sort of finite charge density pretty easy because we just need to study charged black holes in our sort of dual geometry. And as we'll see, disorder is also very elegant to handle in the holographic models as well, although it's a little bit subtle as we'll discuss in some detail. Okay. But the upshot of this talk is that by the end, we will indeed find new stable IR fixed points that have finite disorder, strong coupling, and even finite charge density. And along the way, we'll also sort of point out some subtle issues that had been overlooked in the earlier literature on this topic. Okay. All right. So to sort of say a few more words about the setup of the problem. So the goal is to start with some quantum field theory in the UV. Let's say from a condensed matter physicist perspective, this is already some emergent phenomenon, right? We're not describing necessarily the sort of lattice scale physics, but let's suppose that there's some emergent field theoretic description of the system in d spatial dimensions. So the d here just refers to space and not time. And at various points in this talk, I'll sort of use this notation that pretends we have a Lagrangian for this theory. That's not really necessary, but as a sort of mnemonic, if nothing else, it can be useful. Okay, this quantum field theory does not need to be relativistic or conformal. So we eventually will be interested in field theories that have non-trivial dynamical scaling exponent z. That just tells us that time and space scale differently. So z is 1, for a conformal field theory, and usually larger than 1 else otherwise. And we may also have what's called a hyperscaling violating exponent theta. And you can roughly think of this as like an anomalous exponent for the energy density. And here I'm sort of depicting the role of theta as modifying the entropy density scaling with temperature. So a classic example of this is theta equal to d minus 1 for a Fermi liquid. So system with a Fermi surface where excitations live on some d minus 1 dimensional space in momentum space. Okay, so we want to start with this theory and add disorder. Disorder will be added in this talk by supposing that the QFT has some scalar operator, which I'll denote with O, and it has scaling dimension delta just defined in this way. So we look at the sort of equal time, different space correlation function and extract a scaling exponent delta. Okay. And the particular kind of disorder that we'll be interested in is called random field disorder. We take the original QFT that I described before and just imagine sort of perturbing its Lagrangian by some linear term in the operator O. So we have integral over space-time of h of x, O of x, and t. And that's not a typo. It's very important in this problem that h doesn't depend on time. So the system sees the same disorder profile at all times, but we will assume that otherwise the disorder profile is sort of random and featureless. So ideally, we have the disorder be zero mean. So the over bar here denotes disorder averaging. And the variance of the disorder profile will be denoted with D. Okay. All right. A little bit more about this disorder profile that we're adding. So if the operator O has scaling dimension delta, then you can do a simple calculation to check that the scaling exponent or the dimension, if you like, of D is this kind of funny looking expression. Let's sort of try to rewrite this expression a little bit by essentially defining a new variable, which I'll call nu. And nu is basically chosen so that when nu is 0, it's sort of like a linear shift of the operator dimension delta. And we choose it so that when nu equals 0, this constant D is actually dimensionless. And sort of in analogy to usual quantum field theory, we would then expect that, if nu equals 0, this coupling D is marginal. And that's sort of where, things might be the most interesting from a field theory perspective. And we might expect, the most interesting kind of flows and fixed points and so on. And indeed, we will say that if nu equals 0, so if we choose the operator dimension just right, that we'll say that the disorder is Harris marginal, okay, when this disorder strength is dimensionless. The disorder is Harris relevant if this nu is positive and irrelevant if it's negative. Okay. And then, yeah, note that theta and z show up in this slightly funny way in these expressions, but yeah, for most of the talk, we'll be focused on the behavior of nu. Okay. All right. So that's the disorder profile that we're adding. And as we mentioned at the very beginning, right, we're going to use holography to try and study strongly coupled theories that have this random field disorder. And the holographic theories that we'll have in mind will always be kind of subsets of, or maybe special cases of some general Einstein-Maxwell dilaton type theory, okay? So we assume that our bulk effective description has, a metric, a scalar field phi called the dilaton, and a gauge field with sort of flux F This is a sort of, by now, fairly standard construction in the field for building theories that have these tunable z and theta exponents. Okay. And the precise choices of alpha and beta just tell you the exponent z and theta that you'll get. One nice feature of this construction is that because we have a gauge field in the bulk, we have a conserved U1 charge in the dual theory. And that was sort of one of the features we eventually wanted our models to have. So by the end of the talk, we'll see that that's indeed a sort of added bonus feature for us. We'll be able to describe sort of disordered fixed points at finite density. For most of the talk, I'll turn the gauge field off, but keep in mind that it will eventually be easy to put it back. Okay. And this EMD theory has a background solution. It has all of these fields have sort of non-zero values on the background, but here I've just written the metric. When you have a non-trivial z not equal to 1 and theta not equal to 0, the metric takes this form, which is a little more complicated than ADS, but maybe not too much worse. Okay. Now, the key point is that, in ordinary quantum field theory, when we want to describe disordered fixed points, we usually have to use something called the replica method. And I'll talk a little bit more about that later when we take a break from holography. But the replica method is, I think, very unpalatable. At least to me, I strongly dislike this. It's very subtle to physically interpret. You have to sort of introduce n copies of the theory and then take the limit of n going to 0. Very weird. One key thing that I think is elegant about these holographic models is that disorder is very simple to add. And random field disorder is a sort of particularly nice thing to do in a holographic model. So to the EMD action, if we want to sort of add the random field disorder dual to our scalar operator O, we'll just introduce some bulk field psi, which is dual to O. We're doing this for sort of technical reasons that if we want to sort of study the dynamics or the nature of the fixed point as a function of its operator dimension delta, we would like some kind of tunable coefficient in the action that allows us to tune delta. In holographic models, this is like the mass of the bulk field. And in these EMD theories, we just need to add a mass that has this dilaton coupling B of phi. So it's known how to choose this B of phi to get sort of any operator dimension that we want. Okay. So, okay. Why disorder is so nice in holographic models is that the UV boundary conditions for our sort of bulk geometry can just naturally encode the specific disorder realization that we're studying. So conceptually, it's a very clean way of handling disorder in a quantum field theory. So the picture is that, we have this scalar field psi in the bulk, which is dual to the disorder field in the QFT. And, in the UV, we choose the boundary conditions on psi to just be, proportional to h of x times whatever at least for non-normalizable choices of delta, times whatever the sort of leading exponent would be for the bulk field psi. And as r goes to 0, that's sort of how we encode disorder. And what this means is thus, to study the disordered fixed points that arise, we essentially need to solve the bulk equations of motion, in the presence of this scalar field in homogeneity. Okay. And so the goal basically for the rest of the talk will be to explain how to carefully sort of analyze the solutions to Einstein equations very deep into the IR in the presence of this disorder. Okay. All right. Now, with that setup, sort of finished, let me describe a bit sort of what we thought the answer to this problem was, I think until a few years ago. So for much of the talk now, I'm going to focus on really the simplest example of this story, which captures many of the key features of the problem. So we're going to study a conformal field theory in 1 + 1 dimension. So z is 1, theta is 0, little d is 1. And I'm moreover going to consider Harris marginal disorder. So this little nu that we introduced before is going to be 0. The bulk model that we need to study is the one written here. It's kind of an Einstein scalar theory. And this mass of -3/4 is chosen to make the disorder Harris marginal. And in 2014, Hartnell and Santos claimed that if you solve for, let's say, 0 temperature geometries in this theory, you'll find that they flow to Lifshitz fixed points in the IR. And these are Lifshitz points where there's no hyperscaling violation. So theta is 0, but the IR value of z, the dynamical critical exponent, does get modified to 1 + d/8. Remember that when nu is 0, d, the disorder strength is dimensionless, so this formula is reasonable. And here the stars just denote the IR exponents. And Hartnell and Santos use sort of both analytical and numerical methods to justify this claim. I'm going to go through the analytical arguments maybe in a sort of mild level of detail, because as we'll see, it's sort of very important to understand exactly what's going on in the bulk to really get the right picture for the fixed points. Okay. All right. So we know the setup now. We have this Einstein scalar theory. The scalar field has disordered boundary conditions, while we take the metric to just look like ADS, in the UV, and then we ask what is the emergent IR geometry. And the first claim that I want to make is that the IR geometry will be essentially homogeneous. Okay, so we don't need to worry about the fact that maybe when we turn on this disorder, you might have thought that disorder could really kind of crumple the IR, the horizon in the bulk. Maybe there's some very complicated description where somehow spatial inhomogeneity plays a crucial role. So the first thing that we'd like to do is argue that that's not going to happen. Okay, so this disorder, whatever it does, at least when it's weak enough, it will maybe change scaling exponents, but not render the geometry inhomogeneous, at least in an interesting way. The reason for this is maybe deceptively simple, but I think this heuristic argument sort of plays out quite well in practice. So suppose that we solve our bulk Einstein equations. So we want to solve, right, for the metric in the bulk. The metric is sourced by this disordered scalar field. And so the stress tensor coming from the scalar field is certainly inhomogeneous. You might think, therefore, that this is going to sort of make the metric strongly inhomogeneous as soon as it's perturbed away from ADS. However, the key observation is that the stress tensor really has a homogeneous piece because it's quadratic in the scalar field. So if the disorder is sort of random at each Fourier mode, there will be a sort of psi of k, psi of minus k mode that contributes to a homogeneous stress tensor, and then a psi of k prime mode that contributes to an inhomogeneous part. And these two terms are of the same order, so they're both of order d. Now, on average, the inhomogeneous part vanishes, okay, because we've taken the disorder profile to be sort of featureless, so only the k and minus k modes have a non-zero average. And what this means is that we can think of this T prime as itself a perturbation to R minus R over 2G equals D times the homogeneous stress tensor. And if we could find the homogeneous solution to this first part, the fluctuating perturbation, spatially fluctuating perturbation, will only sort of correct the homogeneous part at the next order d squared, okay? So therefore, as long as we don't find that somehow the homogeneous part of the perturbation is blowing up and doing something dangerous, we can always take the geometry to be homogeneous. And this is really important because it will now allow us to sort of quantify what this IR geometry is looking like with just a small number of parameters like z and theta. Okay. All right. So if the IR geometry is homogeneous, the next step is to really attempt perturbation theory. So to actually construct the IR geometry, we're going to need to solve the bulk equations of motion.
Andy, can I ask a question about the point you just explained? Hey.
Yeah.
I was wondering, so you're going to do some perturbation in D. Shouldn't we worry that at some point there's some non-commuting order of limits between D and the radial coordinates? Basically, that at some point you get past the radius of convergence of your series in D, such that, in fact, you can't assume that the homogeneous part is sufficient.
Mm-hmm. So, okay, so this is a good question. And I think I'll try to sort of answer this in the next couple minutes. Basically, if you do a sort of brute force perturbation theory, it's going to just completely fail. And so whatever we're going to do, we'll see that we really have to try to resum things in a careful way. Okay, but I'll argue to you that if you sort of do the correct resummation, the effects of D will always be mild. And so, you know, yeah, maybe if this isn't clear in the next like 5 minutes or so, at least how this might work out, then maybe you can sort of chime in again. Yeah. Okay. But for the moment, let's sort of just naively try to do perturbation theory. And we'll start doing this just for the scalar field, right? So we started with an ADS geometry. We have this scalar field that has weak disorder because we want D to be smaller, much smaller than 1. And so it might make sense that somehow the ADS geometry is not too strongly modified, at least at first. So, okay, in the ADS geometry, it's a straightforward exercise to just exactly solve the scalar equation. Each Fourier mode looks like this. The function f is constant at small r and is a Bessel function. I mean, basically, there's some modified Bessel function. I've just extracted the UV scaling as r goes to 0. So using this result, you can show that the homogeneous part of the stress tensor, which we've argued is the most important, you can show that it scales as 1 over r squared using the sort of dr squared over r squared, et cetera, coordinates for ADS. And this turns out to have exactly the same scaling as the Ricci tensor and r times g. So if we look at our Einstein equation, this is actually kind of the most annoying thing that could have happened. So all 3 terms that we need to worry about are in principle kind of equally as important, okay? And it turns out that if you then do a kind of naive perturbation theory on, you know, starting from that Einstein equation, you will get log divergences essentially immediately, okay? So you can't just brute force the perturbation theory in this way. This was done, I think, a long time ago, and people sort of gave up pretty quickly. So the key thing that Hartnell and Santos pointed out is that, you know, actually, if you see this type of log divergence coming from this marginal disorder, we sort of know what to expect from usual QFT. When we see these kinds of logs, right, with our perturbative parameter sitting in front, this is a sign that some critical exponent or some exponent of this theory is being perturbed. And in this case, if it's the time component of the metric that's getting these logs, it suggests that we're getting some non-trivial Lifshitz exponent, okay? And so what Hartnell and Santos showed is that if you kind of cleverly reorganize the perturbation theory for Einstein equations using some Borel resummation trick, you can sort of get a manifestly convergent perturbative expansion, or so they argued, where Z ends up, Z being the dynamical critical exponent here, ends up getting an order D correction, okay? And as written here, if you Taylor expand to first order in D, that's the sort of naive thing, you'll indeed get this log divergence, okay? And so Hartnell and Santos argued that sort of the correct resummation of these logs will give you a Lifshitz IR geometry coming from this Harris marginal disorder, okay? And one thing I'd like to stress is that in holography, this argument already requires a non-perturbative resummation of the bulk solutions, okay? So you can't do a sort of crude perturbation theory in D. You always need to be very careful when handling this disorder, okay? Now, there's actually a puzzle, and I don't think this was sort of noted before this paper of mine with my student Kaushik. But after staring at this problem for a while, we realized that we were unhappy. And what we were unhappy about is the following issue. So here's the bulk action that we were studying. It's this Einstein scalar theory. And in the Lifshitz geometry, the theory has the same mass, -3/4, that it does in the ADS part of the geometry. So we can calculate the IR scaling dimension of this operator. And you find that in this Lifshitz fixed point, the IR scaling dimension turns out to be 3/2 plus 3D/16. Now, with the value Z equals 1 plus D/8, you can calculate what the dimension of marginal disorder, Harris marginal disorder would be. And it turns out to be 3/2 plus D/8. And we were unhappy because 3/16 is greater than 1/8. Okay. So this means that in the IR theory, we actually have irrelevant disorder. And that's sort of alarming because how can irrelevant disorder support a non-trivial fixed point? If the disorder becomes irrelevant in the IR, then we should be able to throw out the scalar field and just get the metric and the Einstein terms in the action. But if that's all that we have, we just get ADS. That's the solution to the Einstein equations. So we sort of thought that something doesn't smell quite right about this Lifshitz fixed point.
And your delta star, you just literally got from computing delta from the -3/4 equals delta minus D minus Z with the Z that you had gotten from the perturbation theory.
Yes.
Okay.
Yeah. And since D is small, this should be reasonable if we have this nice homogeneous Lifshitz geometry. Okay. So that's our puzzle. And we sort of decided we needed to revisit this old argument a little and really sort of ask, is it right? So we couldn't find a problem with step 1, so we'll move on from that. We think that the IR geometry should be homogeneous. But we found a problem with step 2. So in step 2, what did we do? We said that the geometry is ADS. So we solved the scalar theory, or the scalar equation of motion around an ADS background. We found some solutions and we constructed a stress tensor out of those solutions. However, in a Lifshitz geometry, it turns out that there is an important correction to those scalar modes which was missed. And it turns out to even be missed in the Hartnell-Santos kind of resummation method. And it's missed because what a Lifshitz exponent does is it also changes the sort of leading order power law that sort of sets up the rest of the series expansion for psi. So if I look at psi as, at each wave number k, in the Lifshitz geometry, I don't have r to the minus 1/2, or r to the 1/2, I have r to the 1 minus z over 2. This is important because when we look at the stress tensor that this creates, which kind of feeds into the bulk Einstein equations, it turns out to scale as r to the minus 1 minus z, which is, of course, smaller than r to the minus 2, which is our which is what we would expect if the stress tensor was sort of changing the exponents. So this argument sort of indeed suggests that the disorder profile should become irrelevant in the IR, and kind of missing this subtle point that there's a non-perturbative correction to the sort of radial dependence of the scalar fields on top of this non-perturbative resummation that was attempted leads to a breakdown of this earlier argument. So to fix it, we can use a homogeneous ansatz for the bulk geometry, but now we need to solve for this B and Z a little more carefully. Okay. And this is very, very hard to do exactly. So we make a few approximations to sort of simplify things and then check that these approximations are self-consistent. So the first thing we're going to do is assume that B and Z vary extremely slowly. And okay, I won't quantify precisely how slowly they vary, but they vary slowly enough that essentially you can think of starting in the UV and sort of doing the RG, building the bulk geometry deeper and deeper into the IR. And at each scale R, where you're solving the Einstein equations, you can approximately think of the disorder fields that you're integrating out as seeing a kind of homogeneous landscape. So at each value of R, there will be some wave number K that sort of strongly modifies the geometry at that scale R, but then sort of dies out deeper in the IR. So these functions F written here all exponentially decay as R goes to infinity. Okay. So we sort of say at each scale R, we can focus on particular scalar modes. Those scalar modes see an approximate Lifshitz geometry with a constant Z. So we can evaluate the stress tensor in that Lifshitz geometry with constant Z and essentially solve self-consistently the Einstein equations with this type of perturbation. Okay. And using asymptotic methods, we can check that this ansatz is self-consistent. We indeed find a very slowly varying geometry, and this slowly varying geometry has a Lifshitz exponent Z, which takes the form below. So this is a kind of ugly function. It has got a lot of logarithms in it, but what's going on here? So lambda is a sort of UV cutoff, which we need because the disorder is Harris marginal. So there's going to be a log as an ordinary QFT. If log of R lambda times D is very small, then the big log is approximately just D over 8 log R lambda. And the two logs that remain cancel, and we get Z as 1 plus D over 8. So very quickly, we say that you transition from ADS into this sort of Lifshitz-like geometry. Essentially, the moment the disorder, you hit the scale lambda where disorder becomes important. And then you sort of go to lower and lower energy scales. And eventually, you hit an energy scale, which is this RIR, which is 1 over lambda e to the 8 over d. So this is really, really deep into the IR. It's non-perturbatively deep in D, okay? And at this point, you see that the sort of big log no longer can be approximated as linear in D, okay? And at this point, the Lifshitz fixed point ceases to exist, okay? And this is basically the scale where you can see that the Lifshitz geometry is subtly modifying the scalar field profile versus what we had thought it was originally. And at this point, the exponent Z will drift back to 1. Okay. So this is what we claim the true IR geometry looks like. And in a sense, this Harris marginal disorder is marginally irrelevant. Now, from the holography perspective, this is a very non-trivial thing, but I'll now try to argue that in the right language, this is actually just a one-loop effect. But this effect can only be seen by a careful non-perturbative analysis in the bulk. Okay. So we think we now know how to do these careful analyses. So the holographic problem isn't so bad anymore, but it is sort of subtle to analyze everything. Okay. So in the interest of time, I'll try to sort of zoom through this part, but just give you some highlights. So to understand what's going on here, it helps to take a break from holography and to use what's called conformal perturbation theory. Remember that the theory we're talking about is a perturbed CFT. So we do have at least some remnant of the types of Feynman diagrammatics and so on that we know from ordinary QFT. So, okay. The basic idea is that in conformal perturbation theory, we're trying to calculate, expectation values of observables in a CFT that's perturbed by some operator O, right? In this case, the disorder profile. We'd like to evaluate this disorder averaged correlation function. This is very hard because the disorder average also has to average out the partition function, the sort of path integral over the action itself. And there's a sort of crude strategy to avoid this called the replica method, which tells you to think of n equals 0 copies of your theory. The copies are coupled essentially because they all see the same disorder profile. And the way that you essentially get rid of disorder in the replica method, or the inhomogeneity at any rate, is you average over the disorder profile D and you get this replica coupling S disorder. Because the random field disorder profile is the same at all times, this coupling is non-local in time, okay, albeit local in space. Now, in the conformal perturbation theory, the first thing you notice is that in this non-local in time coupling between two disorder fields O, there's a universal contribution to the sort of effective action arising from the OPE of these disorder fields. So sometimes, in this S disorder, we get two of the same replica fields. So two fields on the same replica showing up. They can interact. They have an OPE. And one of the terms in that OPE is basically OO to stress tensor. When you have Harris marginal disorder, it so happens that you get OO goes to stress tensor divided by sort of delta T, right? The time difference between the 2 points. And if we imagine doing the Wilsonian RG, that and integrating out short timescales, this will give us some logarithms in the effective action that we're going to interpret as rescalings of time. So the time coordinate is going to get some additional rescaling proportional to the disorder strength D. This was pointed out in a very nice work in 2018. And in the holographic theory, you can show that this ratio of OPE coefficients is 1/8. So we exactly reproduce the Lifshitz scaling from before. But what was missed is that D also flows under RG. And it took us a while to find what I think is an elegant RG scheme, an elegant argument to actually fix essentially the beta function of D. It's not maybe as obvious how you should do this as it is in usual perturbation theory. But Xiaoyang's argument goes like this. And eventually we fix the change to the disorder delta D and thus obtain a beta function for disorder. And we find that this beta function is positive. So the disorder is indeed marginally irrelevant. Okay. And if you take that beta function and integrate it, maybe writing things in slightly more physical terms, the energy-dependent disorder strength looks like D over 1 plus D times log of lambda over E. It's a kind of standard one-loop effect. And this really reproduces the kinds of logarithms that we see in the holographic calculation. So I showed you Z before, but if you look at D, which is kind of the effective strength of the scalar field in the bulk, it just exactly matches this formula above, okay, with R basically playing the role of energy E. Okay. So this is the way that we now interpret this kind of funny holographic calculation and this geometry that sort of looks Lifshitz, but with this flowing Lifshitz exponent. This is just the one loop flow of the disorder string. And okay, this is maybe a bit of a speculative comment, but I think that what's happening here is that what makes these holographic models very special is that their OPE is very simple. Due to the large N limit and due to the sort of simple bulk theory that we studied, just being Einstein plus quadratic scalar, basically the only important OPE coefficient is OOT. And so I think for that reason, you don't need to sort of think about further corrections to this conformal perturbation theory besides the ones that we showed. I think if you study more general fixed points, you might worry that there are lots of other corrections to this OPE that complicate the story here. But I think at least conceptually for these holographic models, this gives us a very strong justification that we've indeed correctly understood the IR geometry, okay? Because we now also have this field theoretic picture for what's going on, in addition to this kind of intuitive approximate solution of the bulk equations of motion. Okay. So now we sort of have all of the ingredients and we can try to build an honest disordered fixed point in holography. And the key idea is sort of to take inspiration from standard QFT. So in standard QFT, if we look at the phi to the fourth theory in 4 space-time dimensions, right, we get a coupling that's marginally irrelevant. And so the way that we sort of get a finite coupling fixed point, at least perturbatively, is just to go to 4 minus epsilon dimensions. Now, here we're not going to change the space-time dimension, but we can sort of imagine just tweaking the scaling exponent of our Harris marginal field and imagine making it just a little bit Harris relevant. So imagine turning on a field with this exponent, nu, where nu is just a little bit larger than 0. And then we might expect that the beta function for the disorder will just get a sort of linear correction minus 2 nu d, coming from the fact that d now has a positive operator dimension. And this suggests that there's now a flow to a fixed point at finite disorder strength, where the disorder strength at the fixed point, which I've denoted as d star, is 2 nu over d times this ratio of OPE coefficients. The resulting theory you can show would have Lifshitz scaling. So starting from a CFT in d spatial dimensions and turning on this Harris marginal scalar disorder, at least in this kind of holographic setting where we only worry about the OOT OPE, we predict that there is a basically universal IR fixed point with Lifshitz exponent 1 plus 2 nu over d. And this fixed point will be stable. It's the actual IR geometry, and it is a Lifshitz fixed point with finite disorder. Okay. So this is what we believe is sort of the right way to build disordered holographic fixed points. Now, the argument I gave is sort of a field theoretic one, but we can, we started the story with holography, so we can at least check that holography also reproduces the same physics. And using the same kind of intuitive kind of asymptotic arguments that I made before, we can argue that indeed the solution to the Einstein equations will approximately take the form shown here. So we start off with ADS, and then, at some IR scale, which is actually non-perturbatively deep in the IR still, although not exponentially so, we essentially see, not exponentially in D at any rate, we see a crossover to a Lifshitz fixed point. Okay. And this Lifshitz fixed point does indeed have the right scaling exponent. One important sanity check that we can make in these models, and we can make very elegantly in holography, is that at the IR fixed point, if you calculate the scaling dimension of the disorder D, you find it's exactly 0. Okay, so at the IR fixed point, the disorder supporting it becomes exactly marginal, which sort of makes sense. If it was relevant, we wouldn't be at the fixed point, and if it was irrelevant, we would go back to the original CFT. So we now feel that our story is sort of truly self-consistent, and it passes sort of all of our sanity checks. Okay. All right. There are a couple more sanity checks that we've done that I can describe. So one of them is just to compare to other results. So in the literature, a few years before us, there were some condensed matter theorists who studied essentially large N vector models. So these are essentially models with quasi-particles. They're weakly coupled, but they do have disorder that's sort of weakly Harris relevant with an exponent nu that's proportional to 1 over n. And these authors calculated that there's a disordered IR fixed point, and it turns out it has a Lifshitz exponent, which is exactly equal to the one that the holographic models would have. So it's possible that at least for sort of perturbed CFTs, this 1 plus 2 nu over d is a very general result. But I don't think we have a proof of that. It's just, it's so far what seems to be happening. Okay. On the disordered fixed points in holography, we can also, at long last, go beyond the charge-neutral CFT, and we can do this same calculation now in an EMD background with non-trivial z and theta, as well as at finite charge density. And we do the same kinds of analyses that we've done, and we show that there's a flow to a new fixed point where the IR Lifshitz exponent, dynamical critical exponent z, increases, by an amount proportional to nu, and hyperscaling exponent theta doesn't change, at least for these EMD models here. And this is a setting where, at least so far, I think holography is really crucial to do the analysis because we don't have an analog of conformal perturbation theory in this setting. So I think that these are the types of models and analyses where holography becomes really powerful as a tool. Once we have this IR disordered fixed point at finite density, we can start asking some questions that we couldn't before. And one of the questions that we'd like to ask is about the nature of transport at the IR fixed point. In particular, we're going to focus on the electrical transport captured by conductivity sigma. We'll look at sigma as a function of frequency, starting with the 0 frequency limit where we have a DC conductivity. We find that the DC conductivity is very large because the disorder at the fixed point is perturbatively small. It's proportional to nu. And so we get this prediction for the DC conductivity. Okay. The scaling with temperature of this result is consistent with earlier predictions that I made back as a grad student. So that made us happy. Once we know the DC conductivity, we can ask whether there's a sharp Drude peak in the AC conductivity. And this will essentially tell us whether we have coherent or incoherent charge transport in the IR. So here, coherent transport would refer to the fact that there's a sort of long-lived momentum which is responsible for the sort of large DC conductivity that we're seeing. And if we have this coherent transport, we'll see a very sharp Drude peak in the frequency-dependent conductivity. So we do a sort of heuristic calculation, an estimate of this tau, and we find that it should scale this way with temperature. And this calculation makes sense as long as tau is sort of very large compared to the Planckian time. So this gives us a prediction that these IR fixed points have coherent transport essentially when z and theta at the IR fixed point satisfy this inequality. And in other transport regimes, we likely have some kind of incoherent soup, albeit with a large conductivity. I think that's a sort of interesting open problem to explore further. Okay. So that's small frequencies. At high frequency, we can again calculate the conductivities at these IR fixed points, and we find that they have this frequency dependence. The way that the exponents show up is now a little different. This, of course, still only is the case below the IR crossover scale. So we're already in the sort of regime where we're captured, where the physics is captured by the disordered fixed point, but just at high frequency compared to very low temperatures. And we can check that the sort of frequency dependence of this conductivity is also consistent with sort of previously predicted thermodynamic features of these models. So we expect that at the IR fixed point, the charge density should be a dimensionless operator. It shouldn't be something that can change the IR fixed point. That requires this anomalous dimension phi star for the density. And simultaneously, one also then demands that this incoherent conductivity, which turns out to dominate at high frequency, must have this very particular scaling dimension. And if we plug all of our results into this, we find that it indeed is satisfied. Okay. So.
And yeah. Can I ask a question about the DC conductivity? So
sure.
I think your result is that the DC conductivity can continue to diverge as t goes to 0, but there's no longer a sharp peak. There's a regime of parameters where this is happening, right?
Yes, this is what our calculation suggests. It's possible that somehow it may be that somehow you don't quite have a Drude peak, but there's some other sharp peak, but just with a non-Drude form. We don't know for sure. But all we can say is that you kind of don't have this 1 minus I omega t in this when this inequality is violated.
Yeah, I mean the disconnect between the width of the peak and the DC conductivity is somewhat unusual. Usually these go hand in hand for slow momentum relaxation, right?
Yes, I agree. So that's why I think this is likely suggesting some kind of incoherent transport, even if you still have a sharp peak.
So can you quantify better from the DC value what else is scaling with temperature? Because in this sigma DC, there's a tau, but usually the Drude spectral weight has no temperature dependence, so that the DC conductivity scales the same as the width of the peak. But here it seems that there's something that's else besides tau in sigma DC that scales with the peak, that the Drude spectral weight scales with temperature.
So
is it the momentum
way
static
we do the
susceptibility?
calculation, I see what you're saying. The way we do the calculation, we don't see any obvious temperature dependence in. So you might think that if tau is like this temperature dependent exponent, that this K naught, may just have some funny temperature dependence that makes the peak large. Now, in this particular expression, the K naught doesn't have temperature dependence. So maybe you could argue this is sort of too fast, that there's other tau dependence, but we actually sort of we find that from the finite frequency conductivity, this tau is the sort of Drude-like prediction that's coming out.
Yeah.
So I think all that happens is when this inequality is violated, the higher order terms in omega are likely very important, and you just don't have a well-defined Drude peak. This is sort of like my calculation from 2015 on Drude peaks and memory matrices. We did that same calculation here, and we just find that the calculation is only consistent when this equality is obeyed. So something interesting happens when this inequality isn't obeyed, as far as we can tell. But we don't know what it is.
Okay.
Yeah. Yeah. All right. That's basically all I wanted to say. So let me just quickly wrap up. So we found sort of new disordered IR fixed points in holography. And at least for the CFTs, we also now have these conformal perturbation theory arguments to justify the sort of physics at our fixed points. But let me emphasize that especially for these charged models that we've just been discussing, we don't really have a field theoretic method to do this type of calculation. So I think that these holographic methods become very useful in that setting. One remark and one caveat I'd make is that I think that the precise sort of IR exponents will depend on what holographic model you study. We already saw one example of this in our paper. I didn't mention it in the talk, but you can see the paper if you're interested. Okay. And the last point I'd like to make is that the technical methods we've developed for studying disordered fixed points in holography, I think will be very general and I hope will prove helpful in other settings. So with that, thanks for listening.
Thank you very much, Andy. That was a very interesting talk, and we already have some questions in the chat. So let me post the chat question from Petro Mikola. Petro, feel free also to clarify what you were asking.
So I can read. So what repercussions does this insight have for absence of disorder-driven metal insulator transitions? So I think that, I did this work about 8 years ago where we said that, if you take Einstein-Maxwell theory in 4 bulk dimensions, so basically 2 + 1 dimensional boundary theory, that it's not possible to add disorder and reach an insulating phase. And I think that these results are certainly consistent with that. One slight caveat, we haven't actually done, I don't think, the analysis for that particular model, like what the disordered fixed point would look like, just because it's this kind of peculiar limit where z is infinity and theta equals 0. We didn't. I suspect that sometimes that ADS rise to Nordstrom fixed point, you need to be a bit more careful with these arguments. So it's possible that something interesting happens there. But one thing I would stress is that these are all weakly disordered fixed points. So this would certainly be in the metallic regime if a fixed point exists. I mean, it may be that the disorder is relevant and runs away, and then something interesting could happen, but we don't know. But the paper from 2015 has a non-perturbative result in disorder strength. So I'm confident that whatever happens, you don't get to an insulating phase.
Okay, thank you. Petro, feel free to follow up if you have any more questions. Any other questions? I had a thought more than a question, but maybe it can be turned into a question. So when you discussed the dimension of the scalar that you added and thought about how it changes from, like, when you calculated your delta star, I think you called it, like the effect, I maybe call it a effective infrared dimension. That reminded me very much of when you think about holographic superconductors, you can think about the Breitenlohner-Friedman bound being near the horizon, being for a certain scalar field that has a certain mass and is stable near the boundary. It becomes unstable as you go closer to the horizon because the effective mass changes, or really what changes is the dimensionality of your anti-de Sitter space-time, and therefore the Breitenlohner-Friedman bound changes along the radial direction. So I was wondering, so it seems like if you think about engineering your space-time in this way, then you can even come into superconducting phases of it seems like for these non-Fermi liquids, which would make sense because that's what I understand also happens we think in reality.
Yeah. Yeah, I don't disagree. I mean, maybe just one comment is that at least in this setting, of course, it's kind of the opposite direction. So here for these scalar fields, they always get a larger scaling dimension. So it's sort of, yeah, here they always become sort of less kind of less dangerous. But yeah, if you also add a finite density background, I think you can also imagine the sort of opposite physics of the holographic superconductor.
Yeah, I like the way that you were presenting the how to think about this, right? Like this this delta being like really changing between IR and UV, and that's something that I had not thought about. So that's something that maybe one can use to engineer more realistic materials. Just a thought, more than a question. Any other questions? Okay, if that is not the case, we usually hang out for 5 minutes after the recording is stopped. I would like to announce next week's HoloTube. It looks like that's the last one for this year. It's going to be by Marcos Gabiza Amano on rotating fluids and rotating black holes. And it will be at an unusual time. That's why I announced it specifically. It will be at 10 a.m. Central European time. It's 10 a.m. Central European time next Tuesday. Okay, good. With that, thank you again, Andy. Thank you very much. Thanks for the questions, Blaise, and everybody throughout the talk. See you next week.